Last time we ended with associativity, associativity multiplication, which was kind of hardest one to do. Oh, I think someone has their mic on, so could everyone just check their mic, see what background is. So that was that was the hardest property to prove, associativity. But all the other ones are bad. So let's think about distributivity. So if you have, if you're multiplying a matrix by a sum of matrices, it's the same as just taking the product and distributing the product inside parentheses. Can someone tell me why I wrote two distributions? Why do I need to write two distributions? What's different about those two? Are they different? Why are they different? Well, first of all, are they different? Does it matter where you multiply? Yeah, why?
Yes.
Yes, and why is that?
The order matters.
Yeah, the associative, it is associative, but it's not commutative. True, that's also true. The dimensions could be different as well. But assuming that all the dimensions are valid, just plainly multiplying on the left or multiplying on the right are not necessarily the same. So there's two ways you can distribute. One is distributing on the right, and one is distributing on the left. So on the one hand, when you multiply on the left, you're distributing on the left. But if you multiply on the right, you're distributing on the right. So make sure you don't mix them up. We don't have the luxury of flipping multiplication when we want to in matrices. Okay, so we had our definition of matrix multiplication, right, which was the sum. So k equals 1 to k equals n. So the n is the kind of the shared dimension. And let's just remind ourselves, what is the dimension of the first? So when summing up the indices, the coordinates, what dimension are we looking at? What coordinate are we looking at in the first matrix? So what subscripts do I put down for the first one? IK, yes. And for the second one, what do you put down? KJ. Remember, K is the index, and I is the row, and J is the column. And right, you think of the index always is the one in between. Okay, can someone tell me when you sum two matrices, what do you do to the entries? So what are the entries of B plus C KJ? So this one was, yeah, it's a sum of elements, and what elements are they? So if I want to look at the kjth entry of the sum, what entries am I looking at in B and C respectively? Oh, it's not another big sum. The big sums come from the product. So here I'm just adding. Yeah, so when you sum two matrices, all you're doing is summing the respective coordinates. So if I look at the kjth entry of the sum, I want to look at the kjth entry in each matrix and sum them up. Okay. So now, inside my big sum, I have this product, AIK times the sum BKJ and CKJ. Now, what can I do here? What I want to do is I want to split up the sum into two sums. So how do you think we can do that? First of all, the stuff inside the sum is just normal numbers, right? So that has all the nice properties of numbers. I can add them, I can multiply them, and that multiplication is commutative. And the big thing is like I can distribute. So would you agree that we can do this? We can distribute this A term into inside? Yes, so let's do that. So we have AIK BKJ plus AIK CKJ. Okay, so now let's think about what you're doing when you take this sum of terms. Let's kind of write out some of the terms. So let's start from k equals 1. So you have AI1 B1J, and then you're adding AI1 C1J, and then you add AI2 B2J, and then you add AI2C2J, and keep on going. Everyone agree that's how you express the sum out as a big, large sum with a lot of terms? All right, so we know with summing that it's commutative, right? So I can rearrange the order in which I sum things. So why don't I do this? Why don't I take all the ones with A and B together and put that into one sum? So that would be AIK BKJ. So maybe those are these entries. Now let's take all the ones with A and C and put that into one sum. Even use the same index. AIK CKJ. Everyone see what we're doing there? We're just using the commutativity of just normal summation to split this sum into two separate sums. Everyone see that? So this is a property of the sigma notation, which we're essentially just proving here, is that sigma notation is distributive. So what are entries in this matrix? Sorry, these are the entries of which matrix? That is the definition of matrix multiplication for what? What matrix has those as its entries? AB, yeah. And what matrix has this as its entries? AC. So we proved it. So as practice, why don't you try doing the other way? Why don't you try multiplying on the right? So the same thing that happens, but all these things are kind of reversed. So that's nice. That means that we could either do two multiplications and add them, or we can add them first and then multiply. So notice that this is also, what's the opposite of distributing? So for addition, you have opposite of addition is subtraction, opposite of multiplication is division. Like what's opposite of distributing? Yeah, factoring. So I think this is the kind of kind of more useful thing about distribution is in factoring. So if you have a sum of things with a common matrix factor, that could be factored out. So this is matrix factoring. So also useful. All right. So these are just properties of matrix multiplication. Any questions on that? All right. So let's talk about the identity matrix. All right. So let's just give a definition of what this is. The identity matrix is the matrix multiplicative identity. So it's the matrix such that when you multiply it, you don't change the matrix. So that's the definition of the identity of a matrix. So the identity, the multiplicative identity matrix. All right, so if that's just our definition, what are some consequences of the dimension? All right, let's say A is m by n. So if I have A times I is equal to A, and A is m by n, and A is m by n, well, what dimension must I be? Well, it's n by something. Yeah, I would agree. So let's think about this. So it would have to be n by n, right? Because, yeah, because the dimension of this would need to be this, right? So it does need to be n in the first position, and the product's dimension has to be that kind of the outer dimensions. However, let's think about I times A. If A is m by n, and A is m by n, what dimension must I be in this case? M by m. Right, because here you want these to match. And the outers would equal that. So, okay, so what we have here is that so I depends very heavily on the dimension. So let's think about what this I must look like. So if you have AI is equal to A, let's think about what the entries of I must look like. So let's think about AI ij. So a little laggy right now. All right, so we're summing from k equals 1 to whatever the shared dimension is. Let's call it n. All right, so, sorry, I think my laptop's kind of overheating. Okay, so we have so what entries are we looking at in A? IJ or IK? And then what entries would you look at in I? KJ, yeah. All right. So by the definition of the identity, what must this whole sum equal? So what is the entry of IJ AI? Yeah, it should equal what entry should equal a what? IJ. So let's think about the sum. Let's write it out long ways. So we have a we have AI 1 I 1J plus a I2 big I 2J. And at some point, we get to the entry that we kind of care about, AIJ. AIJ. And now what is the corresponding entry in identity that we would be looking at? So at the jth term in the sum, well, I in the column entry in I is always fixed as J. And the row entry is changing. So it wouldn't be JI, but J something. Not IJ either. Well, what is K? It is KJ, but what is K in this case? It's JJ. Yeah. See, so I'm writing out the sum long ways. And I wrote the first one, the second one, and a lot of other stuff. But at some point I get to the J entry. So when K is equal to J. So maybe what would the next one be? What's the next one entry after J in the sum? Yeah, J plus 1. And then J plus 1, J. So I guess we could even go one all the way to the end. What would the last entry in the sum be? So the last one would be, sorry, my computer is just not responding to me. Yeah, it would be AIN, and what would the I entry be? The big I entry. NJ, yeah. So sorry about this. The AIN and NJ. Why does the A always become A? So in terms of what the definition of identity means is that it's the matrix such that when you multiply by A, you just get A back. So it's like the one in matrix multiplication. So that's what AI is. It's like the times one. Oh, why do I, oh, it's just a notation thing. I think other notations use capital letters, capital A, I, J. I like to use lowercase because capital, this also means something else. When we do something called determinants, this will mean something there, where I don't want to use that notation here since I'm going to use a different notation there. But some people use this for coordinates in a matrix. I think the website that or the Mathematize, I think they do capital. Why is N the last one? Is because that's the that's where summing up until, yeah, K equals N. So what is N is this shared dimension. Yeah, so yeah, no problem. So let's think about, so this whole sum, this is all supposed to sum up to Aij. And that's kind of like unbelievable, right? It's a lot of things in that sum. And this is saying for every single matrix, you know, of appropriate dimension, that for every single entry, this is going to add up to Aij. Now that should seem kind of weird, but why don't we treat every single A as variables, just to think about kind of what's going on. Right, because if this is true for every single A, that means every single entry can be every real number imaginable. And that kind of seems unlikely, right? Unless what? Like, so if this is all summed up to Aij, and if you imagine everything else as variables, what do you think the entries of I would need to be to even make that possible? First of all, do you see an Aij in the big sum? Yeah, that's here. Now, what would be really nice if this entry was 1? If this entry was just 1, like the number 1, that'd be nice, right? Because then we would have a 1 Aij here. So what else would be really nice? If that was a 1, and I want this whole thing to sum up to just Aij, what do you think the other entries you would want to be? Yeah, you'd want them to be 0. What happens if these are 0? yeah, what happens? Only Aij is left. So, and that works. So let's make that our identity. So the identity matrix of dimension n is defined as so we're going to define it based on its coordinates. So it's going to be 1, or let's write it like this maybe. Ij. So the entries in the identity matrix is going to be 1 or 0. What's the relationship between I and j for it to equal 1? Which entry gets a 1 in that big sum? The jj, yeah. So what's the relationship between the row and column when it's jj? Well, if they're equal, right? So we're going to put a 1 when the row is equal to the column. But if the row is not equal to the column, then we're going to put a 0. Does that make sense? So let's say what this looks like. So let's look at I3. Yeah, so let's look at I3. What goes here? What goes in the first entry? What goes in the 1-1 entry? So in the 1-1 entry, I is equal to j. So you get a 1. So you read the indices. So how about the 1-2 entry? Is the row equal to the column? That's it gets a 0. 1-3, 2-1, 2-2. Right. Since the row is equal to the column, it gets a 1. 2-3, 3-1, 3-2, and 3-3. So another way of saying it is it's the matrix, the n by n matrix with 1s on the diagonal. We'll call it the I equals, let's say I equals j diagonal. I'm not sure if I defined diagonal yet, but here it is. So the entries where I is equal to j. So that is called the diagonal. And zeros everywhere else. All right, let's just make sure that, let's just try to multiply it by something and make sure we get this same thing back. A, B, C, D, okay. So what's the first entry? So doing the the product. So it's going to be 1 times A plus 0 times D plus 0 times G. So notice that even let's just think about what that means. And this will be something that we'll do in 1.5. Regardless of what these entries are. So do you agree that the first row of the left matrix determines the first row of the result? Do you see why that's true? The first row of the left matrix determines the first row of the result. The second and third rows, they could be whatever you want it to be, and the first row would always be the same. So changing the second and third, oops. It's hard to type when computer lags. So changing row 2 and row 3 in the left matrix does not change row 1 in the result. What's the respective statement for if I change the second and third columns, what doesn't change in the result of the right matrix? Think about columns now. So if I change up C2 and C3 in the right, think about the matrix multiplication. What wouldn't change? So in the first column, let's say first column here, what entries in the second matrix produce the first column in the product? It's only the first column. So it's a neat little trick. So the idea here is that since we have 1, 0, 0 as our first row, that means that in our result, since we have the 0, 0s here, none of the terms under the first row play a role, right? Because those will always output 0. So our first row is automatically ABC. Because there'll always be a 1 in front of like A, for example, and then 0D, 0G. And then the same thing, there's going to be a 1B and then 0E, 0H. So similarly, if you look at the second row, there's a 1 in the second position. So that means only the second position in the column will get a 1 and the rest is 0. Similarly, in the third row, since there's a 1 in the third position and 0s everywhere else, the third entries in the column will get a 1 and 0 everywhere else. So good. So I'll let you kind of do the same thing for IA. But it's the same, pretty much the same proof, but the I's will be on the other side. That's good. However, when we say, one thing I just want to say, when we say identity, we want the left identity to equal the right. So in these cases here, we had different i's here. If we want those to be the same, what would the dimensions be if those two i's were the same? If I want those two i's to be the same thing, what does that say about the dimension of A? Can someone say? If I want to force the dimension of I to be the same, by consequence, what must dimension of A be? So I want to say I want to multiply the same thing on the right as I do on the left. Then yeah, it must be square. So if I want identity that works both on the right and the left, it only works for square matrices. And that's what we will define the identity as, only for square matrices. So I3 is the unique 3x3 identity. Okay. So let's talk about, so when you talk about identity, when you're developing algebra, you want to think about like inverses. So when you think about inverse, so first of all, like, when you talk about inverse of a number, what's the multiplicative inverse, let's say, for a number? How do you define that? Multiplicative inverse. Of just a normal number. What is the multiplicative inverse of a number? Yeah, so we say it's 1 over A. And the way to say it, is that it's the number such that when you multiply it, you get the multiplicative inverse back. So we're going to use that same language when we talk about matrices, is that when we say that B is the inverse of A, if AB is equal to I. So where I is this nice matrix. And we want to work both ways. So multiply on the left and the right, give you I. Okay, let's talk about dimensions. Based on this definition of inverse, what is the only dimension of a matrix that could even have an inverse? So I is, so let's say A is m by n. And if I multiply it by B, well, let's say it's m by n, and we have I. What dimension must B be if I want to multiply A on the left? Okay, n by m, right? Good, because we want a square matrix. However, what happens when you flip it? You want BA to also be m by n. See that it only works if m is equal to n. I want the same matrix that pops out, the I matrix. I require these things to be square. So this only makes sense in square matrices. Okay, so oh yeah, so yeah, so in this case it is n by n, but I'm using the same I. So the idea is that these, I guess, four things need to be the same. So even write it like this. That AB is equal to BA, is equal to the identity. Okay, so now in general, this is a very hard thing to find. We'll develop a way that makes it easier to find. In general, not all matrices even have an inverse. And let's kind of, I think we can come up with matrices that don't have inverses just based on the definition. So let's think about in functions. What function is identity? So if I have f of x, y, and I have 1, 0, 0, 1, the f of x, y is the do nothing function. So what's another way I can say inverse? So if I have g of x, y, g inverse is the undoing function. Right, so where that, so g composed with g inverse is equal to this, this identity. Both ways. So we can figure that out. Let's just do an easy one. This is the 90-degree rotation, right? Counterclockwise. What do you think you need to, we'll just say in words, not in terms of matrix. How do you undo a 90-degree rotation? You just forget about matrices for now. How do you undo a rotation? Any rotation? Yeah, just rotate the other way around. So what is the inverse of the 90-degree rotation? It's the rotation clockwise. So in the matrix, you'll see this in the homework. But this is the rotation matrix. So if you plug in negative of the angle, that'll get you clockwise. So if you plug in negative 90, you get that. And yeah, and just check, does this make identity? What's the first entry going to be? What's the first entry going to be? Do this multiplication now. What's the first entry? 1. Yeah, you get a -1 times -1. What's this entry here? In the 1, 2, 0. Entry in the 2, 1. 0. And entry here in the 2, 2 is 1. So yeah, and the nice thing about functions is that if you kind of just understand what the function is, some of these things like identity and inverse come about. How about the X reflection? How do you undo an X reflection? So first of all, what is that? It's, you negate the Y, right? So that's 0, -1. Nope. It's 1, 0, 0, -1. How do you, if you reflect over the x-axis, how do you get back to where you started? It doesn't even have to be x-axis reflect, it's any reflection. Yeah, you reflect again. So that's an interesting thing that we don't see in normal numbers, right? So that's interesting. So a squared is equal to 1. So that's funny, right? We don't have that in normal numbers. If you have a number squared is equal to 1, what does that mean in normal? I shouldn't say normal, but in real numbers. Yeah, that in real numbers, that means A is equal to 1. But notice it's not true for matrices. You can have a non-1 matrix that squares or even higher powers to a 1. So it's still interesting fact. So really any reflection as a squared is equal to I. All right, speaking of that logic, we have the 90-degree rotation, right? So someone said, how about rotate more? How many times would you need to rotate to get back to identity? 4, yeah. So, so what does that mean? So what do we say the inverse was of 90 degrees? So what was that again? I already forgot. 0, -1, 1, 0 inverse was equal to 0, 1, -1, 0. So what does this mean is that, notice that if a to the 4th is equal to I, that means a times a cubed is equal to I. So that would mean that this is equal to a cubed. Also interesting that its inverse can be a higher power of itself. It's interesting. All right, let's go back to pre-calc. When does a matrix have an inverse? Or sorry, not matrix. When does a function have an inverse? Yes, when it's 1-to-1. And that rule applies even in matrices. Let's think about a function that's not 1-to-1. So I'll tell you the function and you tell me why it's not 1-to-1. So what you do is you take any point x, y, and we're going to shine a light that is at the maybe infinity in the up direction, and we're going to shine it down. And let it hit the x-axis. What is that point if I shine straight down? Can you describe that point? Think of like a projector that it, so it's going to project. That's literally the action we're doing. We're projecting that point onto the x-axis. What point is that? So I'm shining a light like straight on the point towards the x-axis. It would be x0. If this was 4, whatever, this would shine down to 4, 0. So the idea is we're keeping the x the same. Oh, I'm sorry. Handwriting can be bad. We're keeping the x the same, but we're just dropping all the y to 0. Why is that not 1-to-1? So think about that action. Yeah, so both of those are true. So for any point that has the same x, any point that has the same x coordinate projects to the same point. So that's the multiple x. Multiple domain values give you the same y value. All right, so let's describe this function as a matrix. This is in fact linear. Okay, if xy gets sent to x0, let's read that as a matrix. So let's see if we remember how to do that. What goes in the first row? What entries? Oh, by the way, I should have said, this is not 1-to-1. This is not 1-to-1. So what matrix does this action? Sending x, y to just make the y 0. So what is the first row? So the first row are the x, y coefficients of the first one. So there's 1 x and 0 y. So let's read the second row now. How many x's are in the second position? 0. How many y's are in the second position? 0. So the claim is this has no inverse. So just based on it being not 1-to-1, that's kind of reason enough why it doesn't have an inverse. But let's show that kind of explicitly. So if it did have an inverse, there would need to be some matrix such that when you multiply, you get the identity back. Okay, so let's do it. Let's multiply this by A, B, C, D. What's in the first position? The 1, 1 position? So it's 1A plus 0C, right? So it's just A. You see that? And then how about the 1, 2 position? 1B plus 0D. Yeah, so it's B. How about the this one? The 2, 1 position. Zero, yeah. 0A plus 0C. In this last position, 2, 2, also 0. 0B plus 0D. All right, so if this matrix existed, that was the inverse. Can we solve for A, B, C, D? What's the answer? No, you cannot solve for A, B, C, D. Why not? Why aren't they the same? So we claim that they're the same if inverse exists, but why aren't they the same? So yeah, so we could solve for B, right? That means B would have to be 0. Well, that's just 0 is equal to 0. And this is saying that A is equal to 1. But if these two matrices are the same, what does that line say? So there's no linear system here, right? This is just these two matrices are the same, and we have that, we have 0 is equal to 1, yeah. So this is a contradiction. These two matrices can't be the same, because if they were, then 0 would be equal to 1. So this aligns with our kind of intuitive idea why this doesn't have an inverse, right? Because you can't undo this action of shining a light onto the x-axis. All right, let's do an example. Let's say, does this have an inverse? All right, if it did, what would the inverse look like if it did have an inverse? What does it mean to have an inverse? Yeah, so it means that if I multiply this by something A, B, C, D, that what would I get back is 1, 0, 0, 1, right? So let's do that. And now we want to solve for A, B, C, D. Okay. So what do we get in the matrix multiplication? What does the 1, 1 entry give you? Yeah, 1A plus what? 2C about the 1, 2 entry? Right, B plus 2D. 2D, yeah. The 2, 1, that's okay. It's 2A plus C, and then how about the 2, 2? 2B plus D. And this is equal to, allegedly, 1, 0, 0, 1. Okay, so if this is true, what's true about A plus 2C? What is that equal to? A plus 2C equals to 1. What's B plus 2D equal to? 0. 2A plus C equal to 0. And 2B plus D equal to 1. All right, this looks like something, right? What is this? How do we solve for A, B, C, D? We don't need a substitute. Just hint, if you replace A, B, C, D with X, Y, Z, W, what would you do? And what would you do if I put a little bracket? Yeah, it's a matrix. Make an augmented matrix. All right, so what would the first line be? First row. So let's let the columns be A, B, C, D. Yes, there's some zeros in there. 1, 0, 2, 0, 1. What's the second row? Zero, 1, 0, 2, 0. The third? Two, 0, 1, 0, 0. And the last 0, 2, 0, 1. So are we seeing how reapplicative linear systems are? All right, how do you solve this? Which row operation do you want to do? There's only one option, right? Let's do row 3. Minus 2, row 1. So 0, 0, negative 1, 0, negative 2, 0, 2, 0. Why are there so many numbers? Well, it's a 4x4 system, right? We have 4 variables, right? These are the 4 entries in the matrix. And we have 4 equations, right? Because we have 4 things that are true when we did the multiplication, that each entry needs to be the same. So that's why we have 4 equations. Which one is negative 3? Oh, 2, row 1, yeah. Yes, I agree. Do you see why it's 4x4? Or even though I could have put a 0B and 0D, for example, right? In this first one. You don't see it? Yeah, so I could have 0b plus 2c plus 0d. All right, so is that better with the dimension? All right, cool. So what would the next step be? Row 4, right? Row 4 minus 2, row 2. All right, and then this is -3. All right, did you get that one right? Okay. All right, we can solve now, right? What's d equal to? -1/3. What's c equal to? 2/3. All right, b is equal to 2d. Sorry, b plus 2d is equal to 0. So that means b is equal to 2/3. And then what's a? A plus 2c is equal to 1. So a is equal to 1/3. So what is the inverse? It's equal to 1/3, 2/3, 2/3, 1/3. Right, that's it. And we could even factor out this 1/3. That's interesting that just multiplying it by 1/3 gives you the inverse. Oh, sorry, C, oh, my bad. C is 2/3. So I have 4/3 here, so it's, yeah, -1/3. Thank you. Yeah, so that's the definition of the inverse, is that it's the matrix that you multiply to get the identity, which is 1, 0, 0, 1 back. What if it's not 2 by 2? Well, then you have a 9 by 9 matrix right now. But we'll find ways to make this calculation a lot easier, even for 2 by 2s. Sorry, which one gets the, oh, yes, this one was also negative. Thank you. Yeah, I wonder, so there's a formula for this that's very quick, and I knew something was wrong. Thank you. But yes, we will actually develop a formula for this, which you actually could do right now. We can actually, I'll set it up for you, and then you do it. So now you do it. Solve for x, y, z, w. We'll do that next time. Some other stuff. We'll do a little bit of graph theory next time too. But for a big chunk of the for the stuff between now and the midterm, finding the inverse of the matrix will be our main goal. So yeah, but don't, I mean, this looks overwhelming. First of all, it shouldn't be. It's just a linear system, right? Which we've done countless times already. But there is a formula that will develop. I recommend you not just skipping to the formula, appreciate, the process to getting to that formula and doing this out. I recommend try to do this out yourself first, to figure it out. There is one condition. So try to figure out what the condition. At some point, you'll divide. Oh yeah, it's done. We're out of time. Okay, so I'd try working on that. We'll do it next time. But okay, yeah, I'll see you Wednesday, and you have homework to work on. I'll stop recording.